Okay, the speaker is Dr. Meer Ashwinkumar from University of Berlin. So he'll talk about duality and discretization of integral quantum field theory from 4D Chern-Simons theory. So please start.
Thank you for the introduction, and thank you to the organizers for the opportunity to speak. So today I will be describing some recent work of mine done in collaboration with Professor Masahito Yamazaki and Dr. Junichi Sakamoto, and it appeared recently on the archive in September. So you can find it on the archive using this code. So in this paper, what we basically study are certain integrable systems in 2 dimensions, namely integrable quantum field theories. And we study these 2-dimensional integrable quantum field theories from the perspective of a 4-dimensional gauge theory, namely 4-dimensional Chern-Simons theory. So 4-dimensional Chern-Simons theory is a relatively new development. It has emerged as an organizing principle for various integrable systems that live in 2 dimensions. And you may be familiar with 3-dimensional Chern-Simons theory as a topological quantum field theory, since there is no metric in the Chern-Simons action. Here, what we have is a 4-dimensional action. And how we obtain a 4-dimensional Chern-Simons theory is by taking the 3-dimensional Chern-Simons action given by this expression over here, and we wedge it with this one form, which is actually a meromorphic one form given here, defined on a Riemann surface C, right? And here the Riemann surface has complex coordinates z, z bar. So now we have a 4 form over here. And so the entire theory is defined on a product of two manifolds, one of which is C, the Riemann surface on which omega is defined, and the other is a 2-manifold called sigma. Okay. And now this theory is not a topological like 3D Chern-Simons theory. Rather, it is topological holomorphic. It has topological invariance along sigma, but it has holomorphic or meromorphic dependence on C, on the Riemann surface C. So this has a slightly different nature from 3-dimensional Chern-Simons theory, but it has the right properties, as we shall see, to realize the integrable systems of interest that such as integrable lattice models and integrable field theories. And in passing, I will note that in general, we allow the gauge fields in 4D Chern-Simons theory to be complex valued, and therefore the gauge group is also complex, and it is denoted as G. So what kind of integrable lattice, so what kind of integrable models can one realize using 4D Chern-Simons theory? The first example is the lattice models which are realized, the integrable lattice models which are underlaid by the structure of the Yang-Baxter equation with spectral parameters. So there are a large class of integrable lattice models that are integrable because the Boltzmann weights that give rise to these integrable lattice models are elements of a particular matrix known as an R matrix. So you have an R matrix, and this R matrix satisfies what is known as a Yang-Baxter equation with dependence on some complex parameters known as spectral parameters. And the fact that these R matrices satisfy the Yang-Baxter equation ensures that the lattice model is solvable and you can actually compute the partition function of the lattice model explicitly. And the incisive observation of Costello was that 4-dimensional Chern-Simons theory can be used to realize these lattice models. And subsequently, Costello, Witten, and Yamazaki, they used rather down-to-earth physical techniques to study 4-dimensional Chern-Simons theory. In particular, they showed using Feynman diagram analysis that the correlation functions of Wilson lines that are crossing in this form over here, they realize the solutions of the Yang-Baxter equation with spectral parameters. So for example, if I choose the spectral curve C to be the complex plane, just by studying the correlation function of these two Wilson lines, I obtain the known rational R matrix that gives rise to rational integrable lattice models. So all I need to do is I take two Wilson lines in for Chern-Simons theory. I put them along the topological surface sigma, and they are on distinct points on the spectral curve C, Z1 and Z2. And just by computing the propagator and finding the interaction between these two Wilson lines, I see that I can reproduce the known expression for the rational R matrix that can be found in the mathematical physics literature. In particular, it's a rational function of Z1 minus Z2. And here you find the tensor Casimir, which is just the sum over the Lie algebra generators in particular representations, rho and rho prime, which are the representations of the Wilson lines given here. So this is a straightforward computation, and in general, you can consider more general configurations in for Chern-Simons theory. So if on the topological plane sigma, I consider a net of Wilson lines in this form, you can actually see that all the interactions between the Wilson lines localize to these intersections over here. And basically all the interactions build up these R matrix elements at each of these intersections. And now if you just take a trace in this direction, you get a transfer matrix. So you have a transfer matrix in each, a transfer matrix arising from each of the horizontal directions here. And then when I take a trace in the vertical direction, I just get the partition function of the integrable lattice model in question. So what this means is that the correlation function of a net of Wilson lines is equivalent to the partition function of the lattice model. And the integrability, which is underlaid by the Yang-Baxter equation, can be seen explicitly because the Yang-Baxter equation is realized in for Chern-Simons theory explicitly as well. And it is realized due to the topological symmetry along sigma. Basically, if you have these three Wilson lines in this configuration here, and they are at distinct points on the spectral curve C, that means Z1, Z2, Z3, I can move this vertical Wilson line across this crossing over here without encountering any singular behavior or other pathologies, because these three Wilson lines are not really touching each other. And there is topological invariance along sigma. So I can move this vertical Wilson line. And as a result, I realize the Yang-Baxter equation, because say I take the upwards vertical direction to be the time direction, then I find here this is R12, this is R13, and R23. But then over here, going upwards, I start with R23, then R13, then R12. And this is precisely how you get this Yang-Baxter equation in for Chern-Simons theory. So these are known results from Costello, Witten, and Yamazaki's work. And in general, you can consider other spectral curves. C is equals to a cylinder, which gives you the trigonometric R matrix, and you need to modify your meromorphic one form to be dz over z. You can also choose C to be this elliptic curve for some complex structure tau, and now omega is equals to dz. And in this case, you can realize elliptic R matrices, which are elliptic functions of Z. And therefore, the three choices of C lead to the rational, trigonometric, and elliptic integrable lattice models, right? And in fact, you can realize even more structures such as the Yangian algebra can be realized in for Chern-Simons theory in more than one presentation, such as the RTT presentation, but I won't go into that in so much detail today. I will mainly be interested in another type of integrable system, which is the two-dimensional integrable field theories. So far, I have discussed line operators in for Chern-Simons theory. One can also consider surface operators in for Chern-Simons theory. And in fact, there are two classes of surface operators or surface defects. One are the order defects, which correspond to some degrees of freedom introduced at some points on the spectral curve. And therefore, they are described by some Lagrangian on sigma. And the other type of surface defect is the disorder defect, where the gauge field has some singularity at some point on the spectral curves C. So these are the order defects and the disorder defects. And I will mostly focus on the study of order defects in this talk, including their discretization. But eventually, we will observe that due to certain anomalies, disorder defects will emerge when studying order defects. So this is something interesting that we will encounter in today's talk. But let me review how integrable field theories can be derived from Chern-Simons theory. So how do we realize integrable field theories? The simplest way is to couple the Chern-Simons action to a bunch of surface defects at points on C that are labeled by alpha. So you have n surface defects at different points on C, Z alpha. Here I've taken sigma to be R2 for simplicity, but the point is that you have some Lagrangian degrees of freedom given by some fields phi alpha, and then there is also dependence on the gauge fields AW and AW bar in general, and it should be such that the entire 4D 2D coupled system is gauge invariant, right? And this can be done in a number of ways, as we shall see. And what we usually do when considering integrable field theories is we explicitly break the topological invariance along the surface sigma. And this is different from the lattice model situation. So what happens is these surface defects will depend explicitly on some complex coordinates on R2, which if I take the coordinates on R2 to be X and Y, I take the usual complex combinations, W, which is equal to X plus IY and W bar, and then these Lagrangians will depend on these complex coordinates. And this breaks the topological symmetry. And this is fine because in the end, the integrable field theories we're interested in are not topological in nature. And how do we realize the integrable field theory? So for example, one can consider a chiral defect, which depends only on AW bar, and an anti-chiral defect, which depends only on AW. And then there is some interaction between these defects. Okay, you can compute the propagator, and then you can find the correlation function between, correlation function for these two defects. In practice, what one does is one actually just integrates out the gauge fields from the 4D 2D coupled system, and one obtains the 2D Lagrangian, the integrable field theory. And in general, what we usually encounter are chiral and anti-chiral defects, which have some global G symmetry, where G is the gauge group of the Chern-Simons theory. And then the G symmetry will have some corresponding currents, JW and J bar. And these will be coupled respectively to AW bar and AW, right? And in general, we don't restrict just to one chiral and one anti-chiral defect. We can have multiple chiral defects here labeled by alpha and multiple anti-chiral defects labeled by beta. And the general form of the two-dimensional field theory, the integrable field theory takes this form. So you have these terms, these parts of the surface defect, which do not depend on the gauge field over here. So these enter here. And then you have some interaction term, okay? And this can be a rather complicated looking because these are the currents, this J bar are the currents for the G symmetry. And this RAB is just the leading order term in the R matrix that we saw earlier that appears when studying lattice models. So this is actually a classical R matrix that satisfies what is known as the classical Yang-Baxter equation. So this is a rather complicated looking field theory that lives in 2 dimensions. But surprisingly, at least in principle, its equations of motion can be solved exactly because it's actually an integrable field theory. And one might ask, how do we know that it is an integrable field theory from the perspective of Chern-Simons theory? The reason is because there exists a lax operator for this integrable field theory. And this lax operator or lax connection is actually flat. It satisfies this zero curvature equation. And the advantage of using 4D Chern-Simons theory to realize integrable field theories is that the lax connection is just the gauge field. of 4D Chern-Simons theory, or to be specific, the gauge field in the directions of W and W bar. And the flatness of the lax connection is just one of the 4D Chern-Simons equations of motion, which is just this, the flatness along sigma. So the integrability of the field theories are really built into 4D Chern-Simons theory. And the advantage of using 4D Chern-Simons theory is that you do not need to guess the form of your lax connection. It is really the classical solution to your equation of motion for the gauge field. And your lax connection can be identified with the gauge field. But the power of this approach is that once you have a flat lax connection, you actually really have integrability of the field theory. So before I explain how that works, I just mentioned that the lax operator can be computed explicitly as well in 4D Chern-Simons theory, either via a tree-level Feynman diagram computation or just solving for the equations of motion, and it takes this form given over here. And if you just specialize to the case of, say, one chiral defect, one antichiral surface defect, and we focus on C being the complex plane, you actually retrieve the known form of the lax connection for the massless Stirring model or many other integrable field theories which takes this form. So you might be quite familiar with this form for the lax connection, which is the form of the flat lax connection for many integrable field theories. And we can derive this explicitly in 4D Chern-Simons theory. And why we know that this this field theory is integrable. So why we know this field theory is integrable is because once we have a flat lax connection, we can define this monodromy matrix we call W. Okay. So what we do here is we take the 2D theory sigma, the 2D theory on sigma, and we compactify sigma such that sigma becomes a cylinder. It becomes R cross S1. So the spatial direction is compactified, and then we can define this operator, which is the trace of the path-ordered exponential of the integral over the lax operator. And in fact, the flatness of the lax connection can be used to show that this operator is independent of the value of time. That means it's independent of the value of the coordinate along R. And therefore, it is a conserved quantity in the integrable field theory. And this is something known from the study of integrable field theories. What is advantageous in 4D Chern-Simons theory is that this object, which looks like a Wilson loop, it actually is a Wilson loop from the perspective of 4D Chern-Simons theory, because this lax operator can be identified with the gauge field of 4D Chern-Simons theory. So we basically can observe that the conservation of the monodromy matrix in 4D Chern-Simons theory basically corresponds to the ability to move the Wilson loop freely in this R direction, which is parameterized by T. And the crucial point is that this lax operator provides an infinite number of conserved non-local charges for this integrable field theory. And using the Poisson bracket structure of this integrable field theory, we can actually show that these conserved charges are in involution, which means they are Poisson commuting. And this guarantees the integrability of the field theory in question. And of course, what is beautiful in the 4D Chern-Simons construction is that this monodromy matrix, as I mentioned, is just a Wilson loop. So I'll give an example now of a type of integrable field theory that can be realized in 4D Chern-Simons theory. So one natural class of surface defects one can consider is the chiral and antichiral fermions. So if I consider one chiral fermion system, one antichiral free fermion system, where the currents take this form given here, if I integrate out the four-dimensional gauge field, I obtain this integrable field theory. And this is known to be the massless Stirring model, which is widely studied in the literature on integrability. And there are many other models one can realize in this way. But the question that I want to address in today's talk is really, what is the relationship between these integrable field theories that one realizes using these order surface defects with the lattice models we saw earlier? So earlier we saw that using Wilson lines, we can realize integrable lattice models studied in statistical mechanics, just using, if you have many Wilson lines at some point Z and more Wilson lines in the other direction, all at the same point Z prime, I have some integrable lattice model. Is it related in some way to integrable field theories realized using surface defects? And the idea that was alluded to in the paper by Costello and Yamazaki was that if I take the number of Wilson lines in each direction to be very large, basically I take them to be infinity, these Wilson lines will coalesce and combine into surface defects. And depending on the direction on which they are supported, they should give us chiral and anti-chiral surface defects. So this was not shown explicitly, and we wanted to show that explicitly, especially because it is expected that this will give rise to the discretization of integrable field theories and also gives us a framework for the quantization of integrable field theories, which is in general still a somewhat unsolved problem, and it's quite an important problem to solve. So the discretization of integral field theories, which is a byproduct of this study of the discretization of the surface defects in Chern-Simons theory. This discretization is a rather old technique. It's been studied for some time. It was studied by Fadif and Rashetikin, for example, and some other people like Destri and De Vega. So the aim is really to relate these integrable field theories with integrable lattice models. So for example, Fadif and Rashetikin, they were really interested in studying this SU2 principal chiral model, which has this action over here. Sorry, this Lagrangian, I should say. And their approach was to modify the Poisson brackets of the principal chiral model. So these are the Poisson brackets of the principal chiral model, but because of the form of these Poisson brackets having this derivative of the Dirac delta function over here, the discretization is actually obstructed because this term leads to some non-local contact terms when you try to discretize. So what they did was, in an ad hoc manner, they actually removed this obstruction, and then they discretized the resulting model. And this is justified because even when you modify this Poisson bracket structure, the corresponding Lagrangian has the same equations of motion as the principal chiral model. And that resulting Lagrangian, which we shall see in more detail shortly, this is known as the Faddeev-Rashetikin model. So one of the aims of this work was to realize the discretization of the Faddeev-Rashetikin model in 4D Chern-Simons theory. And since I've mentioned the principal chiral model and this problem of non-ultra locality, I should mention that apart from order defects, as I mentioned earlier, there are also disorder defects. And these disorder defects give rise to another large class of integrable field theories. And these are usually of the form of some integrable deformation of the principal chiral model. And this was studied in depth by Costello and Yamazaki in the second part of their paper. And also there was further work done by Del Duque and collaborators where they further elucidated the results of Costello and Yamazaki. And they basically showed that you can understand their results by considering what is known as a formal gauge transformation, where the gauge field is gauge transformed to the lax connection L, where there is no Z-bar component for this lax connection L. And this leads to a unifying action for all the integrable field theories that one can obtain from disorder surface defects in 4D Chern-Simons theory. So here you have the residue of omega appearing quite explicitly. And many integrable field theories have this form, but these are the kind of integrable field theories that are difficult to discretize and difficult to quantize. And this is because this omega is basically phi z times dz, where phi z is sometimes called the twist function. And this twist function will appear explicitly in the Poisson bracket structure of these integrable field theories. And I should mention that these Poisson brackets can also be derived from 4D Chern-Simons theory. And the point is that here you still find this obstruction, this derivative of the Dirac delta function, which obstructs the discretization and quantization of these integrable field theories. So eventually I will show that the theories which have no obstruction can be discretized. And these are the theories that can be realized using ordered surface defects in 4D Chern-Simons theory. But to try to quantize and discretize these non-ultralocal integrable field theories, we will try to use some dualities. We shall try to realize some dualities in 4D Chern-Simons theory, which are known as bosonization dualities. So without further ado, let me delve into the details of the discretization. So the ordered surface defects, as we saw earlier, has this form. Here, the chiral surface defect depends on A minus. So minus here is one of the light cone coordinates. We have the light cone coordinates sigma plus and sigma minus. So I've analytically continued the complex coordinates W and W bar to the light cone coordinates sigma plus, sigma minus. So now once I do that, I also note that the surface defects that I will consider, the chiral one will only depend on the partial minus derivative, and the anti-chiral surface defects will only depend on the partial plus derivative. So now I can actually discretize in a rather straightforward way, because whenever there is a partial minus derivative in the surface defect action, I can just discretize along the sigma plus direction, and I don't need to worry about discretizing this derivative over here. So what this means is I can rewrite the integral over sigma plus as a Riemann sum over lattice points that are equidistant with lattice spacing delta. And this results in a sum of line operators arising from discretization of a surface operator. Here, there's some notation I have used to denote the restriction of the fields to each line operator. And for some convenience, I have defined this one-dimensional Planck constant that multiplies all these actions in this manner over here. So now I have discretized a chiral surface defect. I can also discretize the anti-chiral surface defect because the partial plus derivative enters over here. And then I can discretize along the sigma minus direction, resulting in a sum of line operators given over here. Okay, so now the result is this. I have 4D Chern-Simons theory with n line operators in the light cone direction sigma minus and n line operators in the light cone direction sigma plus. And here I have also discretized the respective path integral measures. And the idea is that now, having obtained this configuration, this light cone lattice of line operators in 4D Chern-Simons theory, where you have the currents also discretized and you have the discrete modes of the currents that are discretized living on each of these edges, I can now quantize the line operators and I can rewrite the path integrals as a trace and a trace over a path ordered exponential. And how do you do that? So this can be done using either geometric quantization or coherent state quantization. The essential idea is that you know that once you have a quantum mechanical system, the path integral can be rewritten as a trace of the time-ordered exponential of the Hamiltonian. And it so happens for these line operators, the Hamiltonian is just the gauge field in some representation. And this is the result of the geometric quantization. And the result is that you get 4D Chern-Simons theory coupled to line operators in which are all in some light cone direction. And the configuration looks like this diagram over here. And so you basically obtain a lattice model. Okay, so because each intersection of the Wilson lines has an R matrix living there, you have R matrix elements at each intersection, and this builds up the partition function of your lattice model. And so the result is that the discretization of the integrable field theory is really an integrable lattice model that one might encounter in statistical mechanics. And there are some details, like, for example, there are some representations of the Wilson lines, and this depends on the specific form of the surface defect in question. So now we have had a glimpse of discretization. So we also want to try to quantize these field theories. So recall that there was the monodromy matrix, which from the perspective of 4D Chern-Simons theory is just a Wilson loop in the spatial direction. And this actually intersects the light cone lattice, okay? So earlier, this monodromy matrix gave rise to an infinite number of conserved charges that ensured the integrability of the field theory at the classical level. Now in the quantum theory, we replace this on-shell gauge field, which is the lax operator, by an off-shell gauge field. And now you have this configuration where there is a horizontal Wilson line piercing through this light cone lattice. And at each of these intersections, you have an R matrix. And the result is that you have a product of R matrices, which is called the total monodromy matrix. So these has alternating inhomogeneities. So this basically is the total monodromy matrix of an inhomogeneous spin chain with alternating inhomogeneities, because when we discretize, we end up with line operators which have alternating inhomogeneities, as long as we start with surface defects at 2 points which are basically different in 4D Chern-Simons theory. So if you have one chiral surface defect at V and one chiral surface defect at minus V, the resulting spin chain after discretization will have total monodromy matrix of this form. And then one can go on to solve for the spin chain using the standard beta ansatz techniques. And the essential point is that when you consider two parallel Wilson lines in 4D Chern-Simons theory, we can use the topological invariance along sigma to exchange the two Wilson lines, realizing the Yang-Baxter equation along the way. And this implies that the trace of the total monodromy matrix for different values of the spectral parameter commute with each other. And this is basically the statement of quantum integrability. And this is the diagram of what I just mentioned. You have basically two parallel Wilson lines, and then you realize the Yang-Baxter equation, or more precisely here, the RLL relation. And this RLL relation, if I take the semi-classical limit of it, it's well known that this realizes the discretized Poisson bracket of the lax connection. And this discretized Poisson bracket is known to be the discretization of the Poisson bracket of the integrable field theory in question. So we have now a nice framework that arises from discretization for the quantization of these integrable field theories. So let me just go into some examples. So earlier I mentioned the Faddeev-Reshetikhin model, and the Faddeev-Reshetikhin model is basically just this. It has this Lagrangian where lambda can be understood as some matrix proportional to one of the generators of the Lie algebra of SU2. That means it's T3 in terms of the usual Pauli matrices. Or more generally, it is a highest weight of some irreducible representation of SU2, or more generally of some gauge group G. All right. This can be realized in 4D Chern-Simons theory. This is the result of my collaborator Junichi Sakamoto together with Fukushima and Yoshida. So from 4D Chern-Simons theory, we can realize the Faddeev-Reshetikhin model using these surface operator, this chiral surface operator and this anti-chiral surface operator. And immediately one might recognize that this looks very similar to some operators that one considers in 3D Chern-Simons theory, okay? Because here the action depends only on degrees of freedom that describe the co-adjoint orbit of this particular highest weight, okay? The point is that the discretization procedure that I mentioned earlier leaves us with this sum of line operators in the sigma minus direction and another infinite set of line defects in the sigma plus direction, where this G and G inverse are just the restrictions of the field G of the surface defect to the respective line operators. And then we can discretize the path integral measure for each surface defect as in a very straightforward manner, as shown here. And the result is that you have Chern-Simons theory coupled to an infinite number of quantum mechanical systems in each light cone coordinate direction. And these quantum mechanical systems are very well understood from the perspective of geometric quantization. One can show that these line operators are equivalent to Wilson lines that are in irreducible representations determined by this highest weight lambda. Okay, so the result is really that you have Chern-Simons theory coupled to these Wilson lines, forming a light cone lattice. And essentially what we have reproduced in this manner is the discretization procedure of Faddeev and Reshetikin from Chern-Simons theory. And this is a satisfying result, but we do not have to stop here. Apart from the surface defects that we have considered here, which we refer to as co-joint orbit surface defects, we can also consider other surface defects. As I showed you earlier, the chiral free fermion surface defects give rise to the massless stirring model. So what one can do is one can discretize the chiral free fermion surface defects to give us 1D free fermion actions. And these 1D free fermion actions, their quantizations are well known. And they are known to be equivalent to Wilson lines in the direct sum of antisymmetric representations of the gauge group SUN. So what one finds is a reducible representation. But if we want to obtain an irreducible representation, we can impose a particular constraint such that psi dagger psi is equals to some constant kappa. And this is well known. If I just impose the constraint such that psi dagger psi is equals to an integer k, then we find that we are focused on only k fermionic excitations of the vacuum, and the restricted Hilbert space then carries the kth antisymmetric representation of SUN. Okay, and this can be further generalized. So if I take my chiral free fermion defect and I add more fermionic fields such that I get a multi-flavor chiral free fermion defect, what happens is I can introduce some further constraints, and I can introduce this term here, which depends on a set of integers, ki, and then the resulting line operator that I obtain by discretizing this surface defect, this can be quantized to give me an irreducible representation that is labeled by this Young tableau here, where these integers k tell us the size of each of these vertical columns in the Young tableau. So what this means is that if I discretize these surface defects, which give rise to some kind of massless stirring model, I will obtain a lattice model where the representations of the Wilson line in these irreducible representations, and then the R matrices are also R matrices which are intertwiners for representations of this type, some irreducible representations. So this gives rise to some very exotic lattice models, and these lattice models from Chern-Simons theory, we can see that their thermodynamic limit is some integrable field theory, which is some massless stirring model with some constraints coming from the constraints given in this action over here. So we can also do something similar in the bosonic case. I won't go into so much detail for the sake of time, but one can basically say that I replace the fermionic fields psi and psi bar by beta gamma systems. So I can rewrite the Chern-Simons theory coupled to the chiral and antichiral surface defects in terms of free beta gamma systems that are gauged. So you have beta and gamma here, and beta bar and gamma bar here. And this is also known to give rise to an integrable field theory when I integrate out the gauge field. And the integrable field theory looks like this for the case of GLN gauge group. And this action includes these auxiliary fields, beta, beta bar. And if I integrate them out, I actually can show that this integrable field theory is just a sigma model whose target space is a product of an odd dimensional sphere with a single free boson. But the point is that if we discretize this free beta gamma system, we obtain this quantum mechanical system, which is basically of the usual form PDQ, where P would be identified with beta and Q would be identified with gamma, and you have the usual commutation relations when you quantize. And you can then show that the coefficient of the gauge field over here, which is mu A, this satisfies your usual Lie algebra relations. So indeed, when you quantize this line operator, the Hamiltonian is really corresponding to some gauge field in some representation of the gauge group. And a convenient approach to studying these surface defects is to choose beta and gamma to be complex conjugates of each other. So I say that beta is Z star and gamma is Z. And then the associated integrable field theory will just be a bosonic version of the Maslach-Stirring model that we saw earlier. And from the perspective of discretization, we know that such surface defects, when discretized, will give us Wilson loops, which are in the direct sum of symmetric representations of, let's say, SUN, if we are considering gauge group SUN. So if we want an irreducible representation, we need to impose these constraints, which is just the analog of the constraint we saw earlier. So here L is some integer, but this constraint will restrict the Hilbert space to the Lth symmetric representation of SUN. And more generally, just like in the fermionic case, I can consider a multi-flavor analog of these surface defects with bosonic degrees of freedom. And with further constraints and a term which depends on these integers L alpha, I will find that the discretization gives me Wilson lines in an irreducible representation determined by this Young tableau, where each row is determined, the size of each row is determined by these integers L1 to Lk. So now we have a method to realize basically any irreducible representation of SUN from discretizing certain surface defects with some constraints, either with bosonic or fermionic degrees of freedom. Recall that when studying the Fourier-Fresher-Tikin model, we could also discretize the cojoint oblique defect and obtain basically any irreducible representation governed by the highest weight lambda. So what this means is that we actually have a seed triality among the 2D and therefore 1D defects, which are the cojoint orbit defect, the free beta gamma defect with constraints, and free fermion defect with constraints. And we can basically use any of these three defects to realize some irreducible representation of SUN, which is determined by some Young tableau. So from the perspective of field theory, we know that the corresponding surface defects realize some integrable field theory, because the thermodynamic limit of the Wilson lines in some irreducible representation now has three different descriptions, right? Either it's a generalized Fourier-Fresher-Tikin model, or it's a bosonic Maslach-Stirring model with constraints, or it's a fermionic Maslach-Stirring model with constraints. And what this means is that the discretization that we have derived implies a triality among three two-dimensional integrable field theories, namely a generalized Fourier-Fresher-Tikin model, a bosonic Maslach-Stirring model with constraints, or the Maslach-Stirring model with constraints. So this is our first main result. And this is a rather deep result, I think, and deserves further investigation. And before moving forward, I will just mention that you can also discretize curved beta gamma systems. And curved beta gamma systems are basically beta gamma systems which correspond to, which describe maps from the surface sigma to some target space X, which is usually taken to be scalar. And the field beta is a 1,0 form valued in the pullback of the holomorphic cotangent bundle of X. The point is, now from such surface defects, you can realize integrable field theories with target space X, which are basically any scalar target space. So the coupling to the 4D Chern-Simons gauge field in this case is via certain holomorphic vector fields on X. And the point that I want to make is that these surface defects given here, these curved beta gamma defects, once you discretize, they basically give rise to line operators in infinite dimensional representations of the gauge group. So now we have some even more exotic lattice models that arise from Wilson lines in infinite dimensional representations. So far we've seen that discretization leads us to a lot of interesting results. It also leads us to a framework for quantization. But for the question of quantum integrability, there is more that one needs to take into account. In particular, the chiral free fermion order surface defect, it's known that the measure of the surface defect is not invariant under gauge transformations. In fact, the gauge anomaly, or rather the chiral anomaly, is widely studied, and it's available in textbooks. You can find and show that the measure transforms in this manner if the gauge transformation parameter is epsilon. So now the entire 4D 2D couple system is no longer gauge invariant at the quantum level. So there is something we need to do to restore gauge invariance. So the trick to doing this is actually to modify the 4D Chern-Simons action, because we know that for general one form omega, the 4D Chern-Simons action transforms in this manner given here. So it is an unpublished result of Costello and Yamazaki that if we shift omega by this quantum correction here, where ZL and ZR are the positions of the chiral and anti-chiral surface defect, then gauge invariance is restored, right? Because the non-trivial variation given here coming from the chiral and anti-chiral surface defects will cancel the non-trivial variation coming from this term over here. And then you restore gauge invariance. And more generally, one can do this for not just free fermion defects, but basically all the order surface defects I showed you earlier, which is, let's say, the cojoint orbit defect, the free fermion defect, the flat beta gamma defect, the curved beta gamma defect. All of them admit this kind of anomaly inflow mechanism, because all of them support affine catch-Moody algebras. And the point is that when your surface defect supports an affine catch-Moody algebra, you can actually detect the gauge anomaly by using the standard OPE of the affine catch-Moody algebra, and you can eventually show that the anomaly has the same form we saw for the free fermion defect, except that in front of the anomaly, you have the level of the affine catch-Moody algebra appearing. So what one does to cancel this anomaly is one modifies the meromorphic one form in such a manner given here, where in the numerator of each of these terms, you find the levels of the affine catch-Moody algebra for that is realized by each surface defect. So this is another important result, but this is of course not a result that was discovered by us. It was already discovered by Costello and Yamazaki, but for details of the calculation, I welcome you to look at the paper. And we also basically showed the cancellation explicitly. For example, here the variation is localized at the simple pose, giving rise to these terms, and the cancellation is shown precisely. The crucial physical implication is that whenever one considers order surface defects, one is eventually guided to considering disorder surface defects, because the anomalies associated with the order surface defects eventually led us to correcting the meromorphic one form in such a manner over here, which can be rewritten as this. So the one form, omega f, can be rewritten in this form, where you now see that omega f has the poles at z plus and z minus, and zeros at zeta plus and zeta minus, right? So this is a result of the anomaly, and you see now that you have disorder defects emerging because at the zeros of this meromorphic one-form omega, the gauge fields must have some singular behavior to ensure that the action and path integral of Foddy Chern-Simons theory are well defined. So now we can actually compute explicitly what these zeros are, and these zeros take this form with some dependence on h bar. And you can actually see that in the semi-classical limit where h bar goes to 0, the poles and the zeros will cancel each other. And this implies that the quantum correction that we saw earlier pair creates a pair of poles and zeros of the one form. And this is essentially what I meant by emergence of disordered effects in the presence of ordered effects. And there is an important implication of this emergence of disordered effects. And this is essentially the bosonization that I mentioned earlier. So in this setup, we are not going to consider discretization. Rather, we're going to consider the equivalence of surface defects without considering their discretizations. So this will also involve the gauge anomaly we just had a look at. And in particular, how we do this is to show that by starting with the free fermion surface defect, we can compute its effective action. And then the effective action will have some description in terms of some bosonic variables. And this effective action, we shall actually call it an edge mode action, because from the Foddy Chern-Simons perspective, it really is an action for edge modes at the poles of the meromorphic one form. And furthermore, this edge mode action can be shown to be equivalent to what is called a WZW surface defect. That means a surface defect with a WZW action. So the diagram is basically this. You have equivalence between free fermion defect, an edge mode defect, and a WZW defect. So the idea is that because of the equivalence between these three defects, in Foddy without even before considering Foddy Chern-Simons theory, we have this equivalence between these three surface defects. But because we can embed these three surface defects in Foddy Chern-Simons theory in a gauge invariant manner, and then we can use the Foddy Chern-Simons theory construction to derive three separate integrable field theories that will all be dual to each other, resulting in a triality. All right, so that is the main idea, and I will just delve into some details quite quickly. So the free fermion defect, the chiral free fermion defect, say when you have a multi-flavor chiral free fermion defect with K plus fermions, this can be rewritten as an edge mode defect where we set K plus to be equals to NF. And here, this edge mode defect will actually take the form of WZW action. And likewise, for the antichiral free fermion surface defect, it also has the form of some kind of WZW defect. The explicit form is given here. So this is what we call the edge mode defect. There's some counter term we need to include over here. The details of these are not so important, but the point is that these degrees of freedom G are not independent of the gauge field. Actually, A minus is equal to G inverse partial minus G and Z plus. And for the antichiral case, A plus is equals to G inverse partial G. So these fields G are not really independent of the gauge field. And so the edge mode defect is of a slightly different flavor from other surface defects. But one can show the equivalence of the edge mode defect to what is known as the WZW defect. And this is using the Polyakov-Weichmann identity. And this is basically a result of Polyakov and Weichmann from many years ago, from the 70s and 80s. Basically, you can show that the edge mode defect is equivalent to this WZW defect. And the antichiral case, you also have an antichiral analog of the WZW defect, where these fields G are now actually independent of the gauge field A. And using these WZW defects in Foddy Chern-Simons theory and basically integrating out the gauge fields, you can expect to obtain some integrable field theory. And I should mention here that you also have the usual currents of your WZW model appearing explicitly in these terms over here. These are some details, but the point is that you have a gauge invariant 42D system. And now the point is that we want to show that there are three equivalent integrable field theories. I will just quickly sketch how this is done. But the main point I want to mention is that these edge mode defects can also be understood as the formal gauge transformation, as arising from the formal gauge transformation as certain Dirichlet boundary conditions of 4D Chern-Simons theory. So that's why in the earlier diagram, I had written here Dirichlet boundary condition and formal gauge transformation. So basically starting from these chiral and anti-chiral Dirichlet boundary conditions, I can perform a formal gauge transformation, which takes us from the gauge field to the lax connection, where there is no LZ bar component. And what I will find is that the 4D Chern-Simons action is transformed as such, where this term over here is a West-Zumino 3 form. And the crucial point is that the lax connection is transformed to some flat connection of this form at each of the poles. And these G plus and G minus are just the value of this G hat, the gauge transformation parameter at each of these poles. And now these two terms over here can be written in this form using the Cauchy-Pompeo integral formula. And using these constraints, I can then rewrite that expression in terms of the edge mode action. So this is the edge mode action we saw earlier. And then these we know are equivalent to the free fermion defects. But this action, this edge mode action, can be used to define, to derive an integrable field theory using the techniques of Costello and Yamazaki. And this field theory that one obtains from these edge mode dynamics would be the bosonization of the Maths-Stirling model. And in practice, how this is done is to note that this meromorphic one form that we obtained from the quantum correction we saw earlier, which takes this form, it is a limit of a meromorphic one form that was already considered by Costello and Yamazaki in gauge theory and integrability 3. So we just need to take a limit of this meromorphic one form, which actually has double poles at certain points, and it has and the 4D Chern-Simons theory is considered with non-chiral Dirichlet boundary conditions at these poles. The point is that we just collide some poles and zeros, and then this omega reduces to this omega, and therefore the integrable field theory derived by Costello-Yamazaki using this omega reduces to the integrable field theory for this omega. And the result is that the bosonization of the Maths-Stirling model is just this integrable field theory, which is a bunch of coupled WZW models with negative levels. So these are quite interesting theories, and we have an infinite number of bosonization statements of this type because we can consider any number of chiral and anti-chiral free fermion defects. And then there is one more bosonization of this Maths-Stirling model. And yeah, sorry, I should say that this Maths-Stirling model is a generalized multi-flavor Maths-Stirling model. And we have obtained one bosonization duality of the Maths-Stirling model. And there is also one more bosonization that one can obtain because there is a duality from edge mode defect to WZW defect. And then we can compute the resulting effective 2D theory, which is a bunch of coupled WZW models as well. But the interaction is different, and the levels of the WZW model are now positive. So now we have two bosonization dualities for the multi-flavor massless Stirling model. And basically, we now have a triality, which relates the generalized multi-flavor massless Stirling model with coupled WZW models with negative levels with a particular kind of interaction, and coupled WZW models with positive levels with a different interaction. And so this is a triality among two-dimensional integrable field theories, and this is our second main result. The hope is that combining discretization of the massless Stirling model as well as the bosonization of the massless Stirling model, we will be able to understand the quantization of coupled WZW models of this type over here, which are known to have this problem of non-ultra locality. So this is not something that we delve too deeply into, but eventually we hope that this can be done. Okay. And in the remaining few minutes, I just want to mention that an additional result that we have derived in our paper is the interpretation of the discretization of surface defects, or in other words, the thermodynamic limit of the Wilson lines in terms of string theory. So the string theoretic interpretation of the thermodynamic limit of the Wilson lines is in terms of the Myers effect or polarization of d-branes. And this employs the realization of 4D Chern-Simons theory in type 2b string theory derived by Kevin Costello and Junya Yagi. And this utilizes a stack of n d5 branes in an omega background. So what you can think of an omega background as is basically a kind of a cigar geometry, and the n d5 branes wrap this cigar geometry, and basically all the degrees of freedom localized to the tip of that cigar. And what we find is that the resulting degrees of freedom are just described by 4D Chern-Simons theory. And this is a result of Costello and Yagi. Basically, you can start with type 2b string theory on this geometry given here, where you need crucially to have a Taub-Nut background, because the Taub-Nut background consists of many cigars which are antipodal to each other. And effectively, the d5 brane will be wrapping one of these cigars, and then the localization takes place and you obtain 4D Chern-Simons theory. There are some details. Of course, you need to include some RR2 form and non-trivial dilaton. For this, I refer you to the paper of Costello and Yagi. But the point is that starting from this config brane setup over here, here you have the omega deformed plane, R2 H bar and R2 minus H bar. Together, this forms the Taub-Nut. You also need to take the 0, 1, and 6, 7 directions to be a cotangent bundle of sigma. And this ensures the topological twisting along sigma. So using this setup, you can realize 4D Chern-Simons theory along sigma cross C. And to realize Wilson lines in 4D Chern-Simons theory, we need to use some D3 branes. If your Wilson lines are the type where the type which arise from bosonic quantum mechanics, you need to consider this setup over here, where the D3 brane is wrapping this cigar, which is also being wrapped by the D5 brane. If you want to realize a Wilson line with fermionic degrees of freedom, it needs to wrap the other cigar, which is not wrapped by this D5 brane. But the crucial point is that both types of line operators we saw earlier, the bosonic and fermionic ones, both can be realized realized from the perspective of string theory. And this is quite a direct derivation. And the point is that now we have these line defects arising from these 3D n equals to 4 theories at the intersection of the D3 and D5 brane. And these 3D n equals to 4 theories, because of the omega deformation, they localize to a 1D theory of bosons. And similarly, in the case of fermions, you also have the fact that the intersections of these D3F and D5 branes are described by these 1D free fermion systems, basically because they are a dimensional reduction of the D4, D6 I-brane system, which is known to be described by n parallel free fermions. So this is how we realize line operators in 4D Chern-Simons theory in string theory. And the point is that if I take many such line operators, which are, let's say, at points in this direction 1, for example, if I say I take this D3 plus B, and I consider many line operators in this direction 1, so these are just points in this direction. If I take an infinite number of them, the Myers effect takes place. And then there's a polarization, which results in these branes having this tube topology, and basically they become a higher dimensional object. And if I consider an infinite number of these D3 branes, I have this cylinder decompactifying into a plane. So in this manner, if I have a very large number of D3 branes in string theory, this gives me a D5 brane. And then I end up with this configuration. And the crucial point is that this configuration in 4D Chern-Simons theory realizes chiral or anti-chiral surface defects. So like, for example, this D5B plus brane realizes this surface defect, which is actually just the beta gamma free beta gamma surface defect, which we saw earlier. And some details can be worked out using Clifford algebras, and you can show that the two line operators, which are in different directions, will give you a chiral and anti-chiral surface defect. This can be shown explicitly. And in this manner, we can show from the perspective of string theory, using the fact that the Myers effect or polarization takes place, that the thermodynamic limit of the Wilson lines give us chiral and anti-chiral surface defects realized by D5 brings, right? So this can also be shown for the case of the free fermion surface operator. And in our paper, we even describe how this works for curved beta gamma defects. More details can be found in our paper. So this is a string theory realization of the thermodynamic limit. It's, of course, quite interesting to investigate further implications of the string theory embedding, especially from the perspective of 4D n equals to 2 theory, the shear sector of 4D n equals to 2 theory, vertex operator algebras, and so on. It's quite a rich story, but I will not delve too deeply into that. I will just summarize the results that I've described today. So we have described how order surface defects in 4D Chern-Simons theory can be discretized to form light cone lattices of Wilson lines. And different integrable field theories can sometimes have equivalent discretizations. This means that they are dual to each other, and this includes instances of bosonization. And we have also shown, following the results of Costello and Yamazaki, how gauge anomalies of order defects are cancelled via the emergence of disorder defects. And then we use this emergence of disorder defects to derive bosonization dualities for generalized multi-flavor massless stirring model, and also a boson-boson duality. And the hope is that the bosonization, together with discretization, would help with the quantization of integrable field theories in general, including the difficult theories, the theories which are difficult to quantize, which are the non-ultra-local integrable field theories. And some future work which I am presently working on is the trigonometric and elliptic bosonizations from 4D Chern-Simons theory. And of course, a long-term project is the discretization and quantization of non-ultra-local integrable field theories from 4D Chern-Simons theory. And so with that, I thank you very much for your attention, and I'm happy to answer your questions.
Okay, thank you very much for very interesting talks.